Assalamualaikum and a very good morning to everyone. Today we are going to present our assignment MAT 575 about interpolation using Lagrange and Newton divided different methods. So, so this is our group members. My name is Nur Miza Atira binti Rosli. Next is Fariha Nur Sabila binti Syahbani. And lastly, Nur Hidayah binti Hashim. We are from N4 CS249 Group 1. We are going to start with the outline for this presentation. Firstly, by using the first dataset, we will discuss interpolation analysis for the first dataset by using the Newton divided difference and Lagrange methods, and then continue with comparison between these two methods on dataset 1 and their manual calculations. Repeat the same step for the second data, and finally end with reference for both datasets. Table 1 shows the planted area and the harvested area of Kelulut B by state in Malaysia for the year of 2021. From the table, we can say that the Pulau Pinang has the smallest planted area, which is 2.85 hectare, and the smallest harvested area, which is 2.75 hectare, compared to Johor has the largest planted area, that is 42.37 hectare, and the largest harvested area, that is 38.09 hectare. That means Johor is the largest state with more land for kelulut farming instead of Pulau Pinang having limited land. The data were collected from the Department of Agriculture 2024 and subsequently analysed by Maple 2023. Table 4 on the slide shows the Newton forward divided difference interpolation method. The table was organized to compute the first, second, third, and fourth divided difference required for the Newton forward divided difference interpolation, and then we can see the result of polynomial here. Table 2 on the slide shows the approximated value of y and the absolute error of Kelulut B by state in Malaysia for 2021 using Newton divided difference interpolation method. From the slide, we can see that the state of Pulau Pinang, Melaka, and Negeri Sembilan are having exactly zero for the absolute error values, which means these three states recorded the lowest value for the absolute error value, while for both Selangor and Johor are having 1.0 times 10 to the power of negative 7, which means these two states recorded the highest value of absolute error values. Table 3 on the slide shows the result of using the Lagrange interpolation method to calculate the value of absolute error. The approximate values closely match the actual data, with absolute errors ranging from 6.6 times 10 to the power of negative 7 to 1.2 times 10 to the power of negative 8. This is the result of polynomial by using the Lagrange interpolation method. Hence, Lagrange interpolation method is used to calculate the absolute error. It gives more accurate approximation. From the table 3, Johor having the highest absolute error with 6.6 times 10 to the power of negative 7, while Pulau Pinang having the lowest absolute error with 1.2 times 10 to the power of negative 8. Here come to the parts where we will discuss the comparison from the result of using the Newton divided difference interpolation method and the Lagrange interpolation method. First of all, we can see from the slide the value of absolute error for the state of Pulau Pinang Melaka, and Negeri Sembilan are not zero when using the Lagrange interpolation method compared by using the Newton divided difference method. Secondly, the value of absolute error for the state of Selangor using Newton divided difference method is 1.0 times 10 to the power of negative 7, while when using the Lagrange interpolation method is 5.5 times 10 to the power of negative 7. Thirdly, the value of absolute error for the state of Johor by using the Newton divided difference method is 1.0 times 10 to the power of negative 7, while when using the Lagrange interpolation method is 6.6 times 10 to the power of negative 7. So, we can observe that the result when using the Newton divided difference interpolation method is consistently compute smaller errors compared to using Lagrange interpolation method.
Next, I will explain the manual calculation using the Lagrange interpolation method. First, we use the Lagrange basis polynomial formula shown on the slide. The values of L sub k x are calculated for each data point starting from k equal to 0 until k equal to 4. Next, we substitute the harvested area values into the formula to obtain the corresponding basis polynomials. After calculating all basis polynomials, we'll multiply each polynomial by its corresponding production value and sum them together. Finally, after expanding and simplifying the expression, we obtain the interpolation polynomial shown at the bottom of the slide. This polynomial represents the relationship between harvested area and Duku production. This slide shows the manual calculation using the Newton divided difference interpolation method. First, we construct the finite divided difference table using the harvested area and production data. The first, second, third, and fourth divided differences are calculated step by step. After obtaining all the divided difference coefficients, we substitute them into the Newton interpolation formula. Next, we expand and simplify the equation to obtain the final interpolation polynomial shown on the slide. This polynomial can then be used to estimate the production value for any harvested area within the data range. Now we move on to the second set of data. This table presents the harvested area and production of Duku in 5 districts in Kelantan for the year 2024. The harvested area is represented by X, while the production is represented by Y. These districts included Gumusang, Machang, Tumpat, Tanah Merah, and Kota Baru. If we look at this table, Kota Baru shows the largest harvested area and the highest production value. Next, I will explain the methodology used in this project, which is the Newton divided difference interpolation method. The first step is to arrange the harvested area and Duku production data in a table form. Then we construct the finite forward divided difference table as shown in this slide. Starting from the origin data points, we calculate the first divided differences by finding the change in production values and dividing it by the corresponding change in harvested area. The same process is repeated to obtain the second, third, and fourth divided differences. The purpose of constructing this table is to determine the coefficients needed in the Newton forward divided interpolation formula. These coefficients are then used to put an interpolation polynomial that represents the relationship between harvested area and Duku production. The polynomial obtained is shown at the bottom of the slide. This equation can be used to estimate production values corresponding to different harvested areas within the data range. Now, I will discuss the result obtained using the Newton divided difference interpolation method. The table shows a comparison between the actual production values and the approximated values. From the result, we can observe that approximated values are extremely close to the actual production values. For example, for Kota Baru, the actual production is 3x6.10, while the estimated value is approximately 3x6.1001. The absolute error is very small, indicating a highly accurate estimation. Similarly, for Machang, Tumpat, Tanah Merah, and Gumusang, The estimated values closely match the original production values. Most of the observed errors are almost zero, which shows that the interpolation polynomial successfully reproduces the given data points. This high level of accuracy is expected because interpolation constructs a polynomial that passes through all the original data points used in the calculation. Therefore, when the polynomial is evaluated at these same data points, the estimated values should be very close to the actual values. The graph illustrates the relationship between harvested area and production as represented by the interpolation polynomial. The blue points represent the original data, while the curve represents the interpolating polynomial. We can see that the curve passes through all the data points, demonstrating that the interpolation model accurately fits the dataset. This confirms that the polynomial obtained from the Newton divided difference method is consistent with the observed data.
On this slide, I present the results obtained using the Lagrange interpolation method. The harvested area data from 5 districts in Kelantan were used to construct a fourth-degree polynomial interpolation function. The polynomial shown here was generated based on the given data points. Using this polynomial, the production values were approximated for each district and they compare with the actual production values. From the table, we can see that the approximated values are very close to the actual production values, resulting in very small absolute errors. The largest error recorded is only 0.000257 in Kota Baru, while the smallest error is 0.0002 in Gua Musang. This indicates that the Lagrange interpolation method provides highly accurate approximation for the dataset. By looking at the graph, we can observe that the interpolated values closely follow the actual values for all districts. The two lines almost overlap throughout the graph, indicating that the interpolation model provides highly accurate estimation. Next, this slide compares the performance of the Lagrange interpolation method and Newton divided difference interpolation method. Based on the results, the Newton method consistently produces smaller absolute errors than the Lagrange method. For example, as you can see at the slide, at Tumpat, the Newton method achieved an absolute error of 0, indicating an exact interpolation at the data point. Overall, both methods provide highly accurate approximations. However, the Newton divided difference method demonstrates slightly better accuracy and numerical performance, making it the more effective method for this dataset. This slide shows the manual calculation process of the Lagrange interpolation method. The calculation begins with the Lagrange basis polynomial formula, denoted as LKX. Each basis polynomial is constructed using the harvested area values of the districts. For k equals to 0 and k equals to 1, the corresponding basis functions are calculated by substituting the non-x values into the formula. The same procedure is repeated until k equals to 4, since there are 5 data points in total. These basis polynomials are then combined to form the final interpolation polynomial. After obtaining all the basis polynomials, they are substituted into Lagrange polynomial equation shown on this slide. Each basis polynomial is multiplied by its corresponding production value and the sum together. This process generates the final fourth-degree interpolation polynomial. The resulting polynomial can then be used to estimate production values for any harvested area within the range of the given data. This polynomial serves as the mathematical model representing the relationship between harvested area and Duku production. This slide presents the manual calculation of the Newton divided difference interpolation method. First, a divided difference table is constructed using the harvested area and production data. The table includes the first, second, third, and fourth divided differences. These divided differences are then substituted into the Newton interpolation formula to form the interpolation polynomial. The detailed expansion and simplification process is shown on the right side of the slide. The final polynomial obtained is very similar to the one generated by the Lagrange method. However, as shown in the comparison slide, the Newton method produced slightly smaller interpolation errors, demonstrating its effectiveness and accuracy for this dataset. In conclusion, both the Lagrange interpolation method and the Newton divided difference method successfully model the relationship between harvested area and Duku production. So, both methods produce highly accurate results. The Newton divided difference method achieves lower interpolation errors and therefore provide the best overall performance for this study.